Welcome to this comprehensive overview of nuclear reactions, a critical topic for the MCAT. In this video, we'll explore the fundamental concepts, types of nuclear reactions, their applications, and how these topics are tested on the MCAT. We'll also go through some practice problems to reinforce your understanding. Nuclear reactions involve changes in an atom's nucleus and are fundamental to understanding both natural processes and modern technology. From energy generation to medical applications, nuclear reactions play a crucial role. Nuclear reactions involve changes in an atom's nucleus, typically resulting in the release or absorption of energy. This differs from chemical reactions, which involve only the electrons surrounding the nucleus. There are two main types of nuclear reactions: fission and fusion. Fission involves splitting a heavy nucleus into lighter nuclei, while fusion involves combining light nuclei to form a heavier nucleus. Let's delve deeper into these topics. Fission occurs when a heavy nucleus, like uranium 235, absorbs a neutron and becomes unstable. It then splits into two lighter nuclei, releasing a significant amount of energy and more neutrons, which can trigger further fission reactions. This chain reaction is the principle behind nuclear reactors and atomic bombs. The energy released in fission comes from the conversion of mass into energy, as described by Einstein's equation, E equals mc squared. This means a small amount of mass can release a large amount of energy. Fusion, on the other hand, involves combining two light nuclei, such as hydrogen isotopes, to form a heavier nucleus, like helium. This process powers the sun and other stars, releasing vast amounts of energy. While fusion has the potential for cleaner and more abundant energy, it requires extremely high temperatures and pressures, making it challenging to achieve on Earth. However, research in fusion technology continues to progress. Another important aspect of nuclear reactions is radioactive decay. Unstable nuclei release particles or electromagnetic waves to become more stable. There are three main types of decay: alpha, beta, and gamma. In alpha decay, an unstable nucleus emits an alpha particle, which consists of two protons and two neutrons. This decreases the atomic number by 2 and the mass number by 4. In beta decay, a neutron is converted into a proton, and an electron, known as a beta particle, is emitted. This increases the atomic number by 1, but leaves the mass number unchanged. Gamma decay involves the release of gamma rays, which are high energy photons. This typically occurs after alpha or beta decay, allowing the nucleus to shed excess energy without changing its atomic or mass numbers. Nuclear reactions have numerous applications in energy production, medicine, and industry. Nuclear reactors harness fission to generate electricity, while medical imaging techniques like PET scans use radioactive isotopes to diagnose diseases. In cancer treatment, radiotherapy uses targeted radiation to destroy cancer cells. The precision and power of nuclear reactions make them invaluable tools in modern medicine. In industry, nuclear reactions are used for material analysis and in devices like smoke detectors, which contain small amounts of radioactive material to detect smoke particles. On the MCAT, you'll encounter questions related to nuclear reactions, including calculations of energy released, understanding radioactive decay, and applying these concepts to real world scenarios. Let's go through a couple of practice problems to see how the concepts might appear. First question: calculate the energy released when 1 mole of uranium 235 undergoes fission, given that the energy released per fission event is approximately 200 mega electron volts. First, convert the energy per fission event into joules. So 1 electron volt is equal to 1.602 times 10 to the negative 19th joules, which is a number you'll need to know for the MCAT. Then 200 mega electron volts is equal to 200 times 10 to the 6 electron volts, which is then equal to 200 times 10 to the 6 times 1.602, and for the purposes of the MCAT, you can just use 1.6, and even some cases just times 2. And that is times 10 to the negative 19, which is equal to about 3.2 times 10 to the negative 11 joules, in which case it would be about 4 if you were to use the 2. Next, calculate the total energy for 1 mole. So we know that 1 mole is 6.022 times 10 to the 23rd atoms, which you can just use 6 times 10 to the 23rd. The total energy calculated per mole is 3.2 times 10 to the negative 11 times 6 times 10 to the 23rd. And this gets you about 1.93 times 10 to the 13th joules. On the MCAT, you'll likely see answer choices that would range from 1 times 10 to the 13th joules, 2 times 10 to the 13th joules, 3 times 10 to the 13th joules, and then 2.5 times 10 to the 13th joule. And so you'll want to pick the answer that's closest to the actual number calculation, which is 1.9 and therefore 2. And so therefore the energy released is approximately 1.93 times 10 to the 13th joules. Let's do another example. This is incredibly important when it comes to the future when going to medical school. Just as a medical student myself, it's incredibly important to understand how decay works. Not necessarily radioactive decay, but half-life decay. Because understanding half-life decay is very important when administering drugs, because it's very important to understand how long will the drug last inside the body through normal metabolism. A sample of carbon-14 undergoes beta decay with a half-life of 5,730 years. If you start with 1 gram of carbon-14, how much will remain after 17,190 years? So first, we have to determine the number of half-lives. And all you have to do is essentially use dimensional analysis to get to half-life based on what was provided. So we know that there's 5,730 years per half-life. So that means that number has to be on the bottom in order for the half-life to then be on the top. So what we need to do then is cancel the years. So all we have to do is take 17,190 divided by 5,730 years, which works out to be about 3 half-lives. Now we need to calculate the remaining amount. After one half-life, half of the original amount is then about zero point 0.5 grams. After two half-lives, one half of that zero point 0.5 grams is 0.25. Then after three half-lives, one and a half of 0.25 is 0.125. So what we really needed to figure out was, in order to understand the actual numbers, we had to find out the number of half-lives. So on the MCAT, you're normally not going to be provided half-lives in fractions or decimal points. It'll generally be a whole number. So it will be pretty easy to suss out 3, 2, 4, and so forth. Of course, that means the other answer choices will also be whole numbers in most cases when it comes to picking the half-life. When it comes to calculation, you always want to round, and that's just going to be dependent on when you do it. Because again, the half-life is a measurement of when it hits that whole number. So one half-life, two half-life, that is when half the substance is gone. The MCAT will not normally test on understanding what half of a half-life is, because that's not what will be important for your future career as a physician. So again, we got 0.125 grams of carbon-14 that will remain. So let's recap. To excel on the MCAT in this space, it's crucial to master the following key points: understanding the difference between fission and fusion, recognizing the different types of radioactive decay and their characteristics, being able to calculate energy changes in nuclear reactions, then applying these concepts to medical and industrial applications. In summary, nuclear reactions are fundamental to understanding many natural and technological processes. By mastering these concepts, you'll be well prepared for the MCAT and beyond. If you found this video helpful, don't forget to like, comment, and subscribe to our channel. Your support helps us continue to create informative videos to aid in your study journey. Good luck studying.